Okay, welcome to the Friday Astrophysics seminar at the Institute for Computational Science. Today, it's my pleasure to introduce Dr. Jorryt Matthee. Jorryt did his master's in Leiden with JWST, and he stayed in Leiden, I think, for his PhD, and is now a Zwicky Fellow at the University of Zurich. So Jorryt is an expert in galaxy evolution, especially galaxy formation at early cosmic times, both observationally, but he also works on computer simulations. So he's a well-rounded astrophysicist. And today he will introduce us to Lyman-alpha emitting galaxies from the epoch of reionization to cosmic noon.
Thank you. While I'm starting my slides, indeed, I prepared a full talk on Lyman-alpha emitters. If people are interested in the simulation part, I actually have backup slides. So, in case you want to hear more after, I'm happy to discuss that. Yeah, it's nice to be here. I'm actually in Zurich as well, so I still feel I'm actually at the venue. So as Robert introduced, I'll talk about observational results of high redshift Lyman-alpha emitting galaxies. And to introduce that, I think it's good to have a bit broader background. Why Lyman-alpha? And the main questions really behind my work are very basic questions: how galaxies form in the early universe. I'm particularly excited in understanding the earliest phases of galaxy formation. And a very related question to this is how did stars and galaxies reionize the universe? I think most people agree now that stars were responsible for reionization, and that the contribution from quasars is likely subdominant. And what's really the key in observable for these kinds of questions is basically young stars. You want to observe young stars in distant galaxies, but stars are continuum sources, and it's hard to detect continuum sources, in particular spectroscopically, if you want to take spectra. And also stars ionize gas around them, and that gas will shine in emission lines, which are typically much brighter. And for that reason, I'm mostly observing emission line galaxies, in particular because young galaxies with young stars will have very strong emission lines. If we want to get a complete census of star formation, I think the best emission lines to use are hydrogen emission lines, so you're not sensitive to metallicity. And very bright hydrogen emission lines are the Balmer-alpha, which is indicated by the red line, and the Lyman-alpha line. The strengths of these lines are related because they are from similar transitions. The H-alpha line, the Balmer-alpha line, is known, particularly in the local universe, to be an excellent tracer of very recent star formation, because it's basically shining when very young stars with ages less than 10 megayears ionize the gas. It's also relatively red. It's 656 nanometers, which means that it's not very susceptible to attenuation, only in the most extreme dusty environments, but in typical environments, the attenuation is mild. On the other hand, the Lyman-alpha line, which is the line I'm mostly studying, this is a line in the very ultraviolet part of the spectrum. That means it's much harder to observe in the local universe because our own atmosphere blocks it. Our own solar system emits Lyman-alpha light. So that's a bit complicated. But for distant galaxies, it's easier to observe because of redshift. This line is intrinsically brighter than H-alpha by a factor 8 to 9, it's nice, but it's very susceptible to dust because it's a very blue UV emission line. And what's particularly important is that the transition is a resonant transition, which means that when Lyman-alpha photons travel through the interstellar medium and also intergalactic or circumgalactic media, they can scatter if there's neutral hydrogen, and this will basically change the way how much and the way we see these Lyman-alpha photons. And just from an observational side, this is the cosmic star formation rate density mapped with various tracers. And if we want to map this with these bomb or emission lines, which are very sensitive tracers to recent star formation. We can do this with H-alpha out to redshift from 0 to redshift 2.5 roughly from the ground. And this is set by the atmospheric emission. At higher redshifts, the H-alpha line is redshifted to the mid-infrared, and our own atmosphere is just too bright. This will change, of course, when we have the spectrograph on the James Webb Space Telescope, which will basically open up H-alpha for all the higher redshifts. The Lyman-alpha line, on the other hand, it's much easier to observe at high redshifts because then its rest frame UV wavelength is redshifted into the optical, where it passes through the atmosphere and where we can observe it with our best instruments. And as you can see here, there's a small wavelength redshift range where these lines overlap. This is about redshift 2. It happens to coincide with the peak of star formation activity. And this is the redshift range that I've been studying a lot to look at galaxies in both these emission lines, because we know that the intrinsic strengths of these emission lines are related. And this is the highest redshift where you can do that. And this will allow us to basically connect our view of the lower redshift universe, where we have much more observables of distant galaxies, to very high redshift galaxies, where we can typically see Lyman-alpha. And actually, for many galaxies, we only see Lyman-alpha. So with this survey, which is called the X-Shooter Lyman-alpha survey, we are studying these questions: what are actually Lyman-alpha emitters? And I will explain this in more detail. We will also investigate how the Lyman-alpha emission lines, what they can teach us about the escape fraction of ionizing photons, which is an extremely important quantity to know, and I'll explain that in detail. The second part of my talk, as I said before the talk started, my talk is a bit modular, so we'll see if I can actually address all these different points, but depending on the time. I have a few slides on case studies of bright galaxies that we have seen in the very, very early universe. One case study on a galaxy that we know that resides in a highly ionized bubble. One galaxy where we can actually see circumgalactic gas around it. And the very recent work, which I'm sure that I'll present, is the work to actually look at the stars directly in such a bright galaxy instead of looking at the emission lines. All right, so about this redshift 2 survey. So the first thing to do is, if you are interested in in understanding what makes a galaxy a Lyman-alpha emitter, is doing a consensus survey, and that's what we did with a double narrowband technique. And what we did is that we observed a part of the sky called the cosmos field with 2 filters. And those filters select emission lines, and particularly H-alpha and Lyman-alpha lines, at a matched redshift. So we can actually select galaxies through H-alpha emission and Lyman-alpha emission blindly and simultaneously. So in this volume of the cosmos field, we can basically see H-alpha and Lyman-alpha for all galaxies. What we see, however, is that in the H-alpha data set, we see this red spatial distribution of galaxies. It's quite a nice clustering. There's actually a protocluster that you can see here. It's actually spectroscopically confirmed now to be a protocluster. If we switch to the Lyman-alpha view, the spatial distribution actually looks quite different, even though this is actually the same redshift and should be the same galaxies. If we also look at the galaxies, the properties of these different galaxies selected in these different ways, they're quite different. So for the H-alpha view, we see 600 galaxies with masses comparable to the current mass of the Milky Way. While for Lyman-alpha, we actually see much lower mass galaxies. And the actual limiting luminosities are comparable for these lines. So what this tells you is that with Lyman-alpha, you pick up much more low mass galaxies compared to H-alpha. And the actual samples for which we detect both these lines directly they barely overlap, even though from principle you expect that they would overlap. What this means is that for most of these H-alpha emitters, which tend to be more massive galaxies, the Lyman-alpha line is too faint. And this means that the Lyman-alpha escape fraction, like the fraction of these photons that are produced, which we can estimate from H-alpha, it's basically very low, so we don't see it anymore. And on the other hand, for these Lyman-alpha emitters, they are typically much fainter galaxies with low star formation rates, and the H-alpha line is too faint. It's a bit unfortunate, and there's only a small overlap in this sample. And the real question basically is why is the Lyman-alpha escape fraction low, or why does the Lyman-alpha escape fraction apparently vary with stellar mass? So that has to do with scattering. So just to explain that a bit, this is a very simple toy picture of a galaxy that we observe. There are stars that in an H2 region, and in this H2 region, Lyman-alpha photons are produced, and they travel towards us through the interstellar medium. And in this picture, the ISM only has neutral hydrogen. There's no dust. The UV continuum photons, they can just travel directly. As I said, there's no dust. Some Lyman-alpha photons may be lucky and actually not encounter any hydrogen along the way. The chance is very low, of course, but there's basically hydrogen everywhere. What's much more likely to happen is that Lyman-alpha photons will encounter neutral hydrogen. Due to resonance scattering, the photons will be absorbed and re-emitted in a random direction and with a velocity shift. And only a fraction of them will actually may actually be in our sightline. What's actually much more likely is that there's actually dust in many of these hydrogen clouds, which means that many of these Lyman-alpha photons that should travel towards us, they traveled a much longer path length because they are scattering in the ISM. They're basically locked or trapped in the ISM much longer than normal UV continuum photons. And that makes the likelihood of being absorbed by a dust particle much higher. And this is the main mechanism why the Lyman-alpha escape fraction is low in massive galaxies where there tends to be dust. This is the basic picture, but quantitatively, of course, this is a poorly understood process. It also depends on many properties like the actual velocities and the spatial distribution. And to try to understand this in a more quantitative way, we have been doing this X-shooter Lyman-alpha survey, which is a survey of 35 galaxies observed with X-shooter. X-shooter is a spectrograph on the VLT, and it's the unique thing about X-shooter is that it covers the entire wavelength range that you can observe from the ground in one go. But the downside is you do it for one galaxy at the time. The resolution is also quite good, the spectral resolution. It's a factor about 4 better than typical instruments used for galaxy surveys at high redshift. And that's nice for Lyman-alpha profile studies that I'll present. So we observed 35 of these Lyman-alpha emitters for about 3 hours per source. And note, we selected only galaxies that we know are Lyman-alpha emitters. So that's a bias in the sample. And what we can do is then see what are the properties of these galaxies and how do these properties compare to other known galaxy population. So I'll present results on the stacked spectrum, because stacked spectrum has a nice signal to noise, and it basically shows the average spectrum of such a galaxy. The average Lyman-alpha emitter, as you can see, it's strongly dominated by line emission. There's Lyman-alpha on the left by selection, and we see other emission lines as well. H-alpha fully on the right, oxygen 3 and H-beta on the around 5,000 angstroms, and a few other features. There are some gaps in this wavelength coverage, and those are due to features of our atmosphere. But the survey was designed specifically such that the wavelengths of these gaps are actually not very important for our science cases. So what we see from this spectrum is that indeed these galaxies tend to have a low mass. Typical Lyman-alpha emitters are actually Milky Way, in terms of their stellar mass, they are Milky Way progenitors. They had the stellar mass that the Milky Way had, likely had 10 gigayears ago. The star formation rate of these galaxies is around 5 solar masses a year, which I think is slightly higher than what are the estimates of the star formation rate of the Milky Way back then. And also what we see from the spectra is that the dust attenuation, as we expect, it's very mild. There's not that much dust, but simultaneously I'll note that this dust attenuation is expected to be low for all galaxies with comparable mass. So what we can already see from this is that while we select Lyman-alpha emitters, which are expected to be dust-poor galaxies, we actually get similar dust attenuations as normal galaxies for these types of masses, which is interesting. Just to go quickly through this, is with all these line ratios, we can show that the galaxies are actually powered by star formation and not by AGN activity. I don't think it's very surprising given their low mass. What is nice is that we can actually constrain the ages from these line equivalent widths. So the galaxies are actually very young on average. And from UV emission lines, in particular helium-2, which is a emission line, it's actually the Balmer alpha line from the helium atom. The ionization energy is 54 electron volts. So you need extremely hard ionizing photons to be able to see this line in emission. We see it very faintly, I must admit. But from the strength of this helium line, we can actually get a very good idea of the stellar metallicity of the stars that power these lines, because you need very hot stars to ionize helium, and stars that are hot tend to be very metal poor. So we can actually get an idea of the metallicity of the stars, and it's quite low. Not unexpected, of course, for high redshift. Just looking at the star formation rate, the star formation rates are similar to the dust attenuation. They are quite normal given the stellar mass. I have to say that actually our star formation rate calibrations may not be applicable to these kinds of galaxies because they depend on the stellar metallicities. If you convert HALPHA luminosity to a star formation rate, there are assumptions there. But if we use the metallicity that we think is applicable, we would conclude that these galaxies are actually quite normal for their star formation rate. They have a normal star formation rate given their stellar mass. So these are not particularly bursty galaxies. Not particularly bursty, not particularly dusty. We can do chemical abundances as well. I'll skip this. What we do see, what is quite unique is that we see, not necessarily unique, but it's quite ubiquitous. We see outflows being present in these low mass galaxies with a variety of tracers. I'm listing 3 of them, and I think all of these independently from each other indicate that there are outflows in the interstellar medium. The first is the Lyman-alpha profile. I'll come back to that later, but the shape of the Lyman-alpha profile is skewed towards the red. You see 2 peaks, and the fact that the redder peak is brighter than the bluer indicates that the Lyman-alpha photons scatter through an outflowing medium. And then in the oxygen 3 line, we actually see broad wings in the ionized. They're broad. There's basically something that broadens the ionized gas, which could be an outflow. And then I think most directly is basically a down the barrel detection of outflows by absorbing interstellar gas, which is blue shifted with respect to the systemic redshift. So all these 3 observations indicates that there are outflows present in these quite low mass galaxies. And summarizing all these different observations of galaxies and comparing them to more luminous galaxy samples at different redshifts, we can try to get the picture of what makes a galaxy a Lyman-alpha emitter. And that's summarized in this picture. On the left, I show a galaxy for which I would say there's a high likelihood that we observe it as a Lyman-alpha emitter, and on the right, the opposite. And there we identified 3 different processes. The first is simple. Galaxies need to be young and they need to have star formation because otherwise they don't emit emission lines. We see actually that the specific star formation rate, which is the relative star formation rate to the stellar mass, is not very atypical. It's quite similar to other galaxies with comparable mass. So this doesn't seem to be the main distinguisher of what makes a galaxy a Lyman-alpha emitter. As I said, the dust attenuation needs to be low, otherwise it's hard to see UV emission lines. But again, the dust attenuation is not extremely low. So it's likely that the third explanation is the most important in determining whether a galaxy is a Lyman-alpha emitter or not. And that is basically that there need to be paths for these Lyman-alpha photons to escape easily through the ISM. There are two ways to do that. Either there are basically chimneys in the interstellar medium through which there's basically no neutral hydrogen or very small column densities, and the Lyman-alpha photons can easily escape through those chimneys. Or just in general, the H1 density is lower, so that there's less scattering events and less, basically that makes the effect of dust attenuation, that makes the likelihood of the Lyman-alpha photons encountering dust lower. So you can have basically those white channels or the color grayscale being different between these two different scenarios. I think it's interesting to speculate a bit on why for Lyman-alpha emitters this is the case, that apparently the H1 column density is different. Well, one explanation is just that it is a stochastic effect. It's just a viewing angle effect, that all galaxies have a similar the similar H1 distribution if you average over all sidelines. But we happen to pick up Lyman-alpha emitter if we look at a fortunate sightline. It could also be that there just simply are more favorable sidelines for galaxies with certain characteristics. For example, galaxies that have strong outflows, they may be able to drive such holes in the ISM, and then therefore we may be able to observe them as Lyman-alpha emitters. And these two things are open questions to be studied in more detail, also by having proper comparison samples. Just to move on, is how common, why do we care about Lyman-alpha emitters? How common are they? And to answer that, I'm actually going to wonder what the entire universe would be, what kind of Lyman-alpha emitter the entire universe would be. We can just simply, instead of looking at individual galaxies, we can basically sum the entire star formation rate of the universe, sum the entire Lyman-alpha luminosity density of the universe, and calculate the Lyman-alpha escape fraction of galaxies in the universe. So you can do that using luminosity functions that are known over a redshift interval. And you can see that the ratio of the Lyman-alpha to the star formation rate density increases by an order of magnitude from redshift 2 to 6. Basically, the globally average escape fraction is around 2.5% at redshift 2, and it's 40% or 30% at redshift 6. So our biased sample at redshift 2, it sits actually here. And what you can see is that it actually is comparable. So even though this is a biased sample at redshift 2, it's comparable to the cosmic mean at very high redshifts at the epoch of reionization. What I think this implies is that if we move from studying galaxy samples at the peak of star formation history, many galaxies will look like the galaxies on the left. But if we move towards the more distant universe, we expect that most galaxies tend to be Lyman-alpha emitters. Their ISM conditions tend to favor Lyman-alpha escape, which means that we can basically predict all these properties, that there will be higher equivalent widths, there will be less dust, the ISM will be more highly ionized, and these fraction of low density sidelines will be higher. And all these things can easily be tested in the future with rest-frame optical spectroscopy. All right, so that's about what makes galaxies Lyman-alpha emitters. Now I want to talk a bit about what we can learn from the escape fraction of ionizing photons using Lyman-alpha profiles. And I need to explain a bit on Lyman-alpha profiles to do that. So, as I said, Lyman-alpha photons scatter. If they would not scatter, we would see a Lyman-alpha profile that would simply be a Gaussian following the motions in the H2 region that emit the photons. If they encounter neutral hydrogen gas, we expect the photons to be redistributed to the wings because of resonant scattering. And if the gas is outflowing, we expect that the redder photons can actually travel through this gas more easily than the bluer photons. So we expect a profile that looks like this. If the gas would be inflowing, this would flip, of course. If we look at the average profile of the redshift 2 galaxies, we see this profile is characterized by outflows. The velocity shift of the red line to the systemic, which is basically the position of the peak, is about 200 kilometers per second. And that's much lower than what has been reported in much brighter galaxies, which tells us that the velocity shift is sensitive to the H1 column density. And this tells us, therefore, that brighter galaxies have a higher column density. What is also interesting is that we actually, if we select galaxies on Lyman-alpha, we actually see similar profiles all the way from redshift 0, measured by HST, UV spectroscopy, to redshift 6, which is quite interesting. And it's nice if you want to use Lyman-alpha profiles to learn something about reionization that I will address. What I want to show here is this main result found by Izatov et al. On the Lyman-alpha Lyman continuum escape fraction. So the Lyman continuum escape fraction basically says how many ionizing photons that stars produce escape from a galaxy. And this is an extremely important property in order to understand which galaxies reionize the universe, because ionizing photons reionize the universe. And it has a long history of being very difficult to measure, particularly at high redshift, where we have the Lyman-alpha forest blocking all that emission. But even at low redshift, because it was found that most galaxies actually don't have a zero escape fraction. Recently, there has been a lot of progress, and there are escape fraction measurements. And what has been found is that there is a very clear correlation between the escape fraction, which is extremely hard to measure, and the peak separation of the Lyman-alpha line, which is actually not very hard to measure. This is the best correlation that has been found by numerous of studies. And this makes it nice because this means that we can get an indirect estimate of the ionizing escape fraction from the Lyman-alpha profile. So we can do that for this galaxy sample. And I'll skip it a bit. And we actually find a few different, it's a bit detailed. I don't have the time to explain all the detail, but I'm happy to explain that if there are questions. There are a few different calibrations, but the calibrations on average agree that for these typical Lyman-alpha emitters at redshift 2, which I've seen are comparable to average galaxies in the epoch of reionization, the escape fraction of ionizing photons is around 5 to 10%, as indicated from the Lyman-alpha profile. And this is around the right number that we need for galaxies to drive reionization. And this is quite a nice result because for a long time, the inferences actually indicates a much lower number. But from these Lyman-alpha profiles, we can change that estimate. Of course, the average number is, I don't think, super interesting. It's nice that it works, but what you really want to know is which galaxies have a higher escape fraction compared to others, because this impacts the morphology of reionization. For example, massive galaxies have a higher escape fraction, and then you expect reionization really to start first in the most overdense regions. On the other hand, if low mass galaxies have a much higher escape fraction, you expect it to be much more homogeneous. Modulo clustering effects, of course. But the galaxy property dependence of the escape fraction is very important. And this is ongoing work to try to map this dependency with Lyman-alpha profiles. Just want to highlight some ongoing results is that while we see this average Lyman-alpha profile that is really well understood with this double peaked profile seen from, which you can explain with scattering only, we see these two galaxies which are showing either a triple peaked Lyman-alpha line, which is this blue line in the middle. That is basically indicating a two-component ISM structure, whereas part of the Lyman-alpha photons actually scattered and part of the Lyman-alpha photons did not. And in this like more extreme galaxy on the right, we actually see that the Lyman-alpha profile is almost the same as the H-alpha profile, which indicates that there's hardly any neutral gas in the ISM from the direction of the stars to us. So these galaxies are really exciting because they indicate high escape fraction of ionizing photons, and we can use these to see what is really causing this. All right, so I was rushing a bit because I want to move on. So I want to move on to a few of these case studies of what we can do at the highest redshift, where observations are very challenging, just because galaxies are very distant and sources are very faint. We also only have a limited wavelength coverage where we can see galaxies, but it's already exciting to show what we can do. Now I'll just go through all these case studies, and as you will see, many of these case studies rely on results, or the interpretation of these observations rely on results that I've shown before. And the first case study is a highly ionized bubble at redshift 6.6. So as I said before, the Lyman-alpha line is used as a tracer of when reionization happens. This is shown in this illustration on the left. When the universe is not fully reionized, when there's neutral gas in the intergalactic medium, whether galaxies reside in ionized bubbles or not will affect how we see their Lyman-alpha line. If a galaxy is in an ionized, fairly large ionized bubble, if a galaxy is in a fully ionized universe, we can see the Lyman-alpha profile exactly how it escapes the interstellar medium as a double peak. If there is some neutral gas, we expect that the bluer peak will be absorbed by intervening neutral gas in the intergalactic medium. So we expect that if we move from redshift 2 to 7, we expect that the profiles change from this to this. This is indeed what is observed. Most Lyman-alpha lines look like a single red peak, likely because the intergalactic medium absorbed the bluer part of the line. If the galaxy is even more neutral and the ionized regions around galaxies are smaller, and this absorption wing moves to the red, and you actually start to lose Lyman-alpha from galaxies. And the way how much this happens depends on the neutral fraction of the intergalactic medium, and it depends on how this line profile emerges from galaxies. But so this is used by doing these kinds of measurements for very large samples of galaxies. People have been using this fact to infer the neutral fraction of the intergalactic medium, in particular at redshifts above 7, where we don't know about that many quasars. So quasar measurements are much harder. Quasar absorption lines are saturated because the neutral fractions are higher than 10 to the minus 5. And above those neutral fractions, the absorption lines from the Lyman-alpha force basically is completely saturated. And we don't have SKA yet, but you want to do something. So people have been using Lyman-alpha lines to do this. So one exciting galaxy that we discovered, actually it was discovered by a Hawaiian team, and we confirmed this discovery, is this galaxy that they called Kola 1. And this is actually the first galaxy for which we still see a double-peaked Lyman-alpha line, even though the redshift is 6.6. So it's an extremely all hydro simulations that are built to study reionization actually predict that those galaxies should not be observable. But that is because they assume a uniform UV background. But what this detection of this galaxy, of this Lyman-alpha line means, that this galaxy resides in a highly ionized bubble. We can put a lower limit on the size of this bubble based on the velocity out to which we see it. And what is interesting is that, as I showed before, the peak separation of these Lyman-alpha lines is a tracer of the ionizing escape fraction. So what we can do is for this galaxy, we can actually measure the ionizing escape fraction. So you can measure the contribution to the local UV background from this galaxy, and then work out if this is enough to ionize this region. It turns out that it's very unlikely to be enough. So even though we know that this galaxy resides in an ionized region and we can quantify its own contribution, we know that there need to be more ionizing sources. And to try to find those, we got awarded a James Webb program to blindly search for galaxies in the ionized bubble with the GRISM spectrograph. So we will find all galaxies out to some star formation rate limit, and then we can address whether those galaxies. So we can either find the scenario on the right, that we see that there are some moderately bright galaxies around this galaxy, basically an overdensity that helped ionizing this bubble, or we can actually not find that, and that actually may mean that the ionized bubble is actually driven by unseen, even fainter galaxies. So you can indirectly learn something about which galaxies reionize the universe from this set of observations. At least that's the hope. The second case study that I quickly want to show is another galaxy at the same redshift. It's not the same galaxy, but at the same redshift. The reason why it is at the same redshift is that we can actually find galaxies at that specific redshift very well for atmospheric reasons. But what we saw for this galaxy, this is a triple merger. This is an HST picture of the galaxy in the background. So there are 3 UV complexes within 5 kiloparsecs from each other. They're all confirmed at the same redshift, so there's not a projection effect. The contours actually show carbon-2 line emission, which is basically showing cool gas seen by ALMA. It overlaps with the stars mostly. And it's a very complex structure. We see 3 UV sources, 1, 2, 3, 4 sources of cool gas emission. So it's a very complicated structure. But what we went to do with MUSE is that this galaxy is a known bright Lyman-alpha emitter. The Lyman-alpha line is here. With the MUSE IFU, you can actually with a very good sensitivity search for extended emission. And that extended emission could show neutral gas around the galaxy in which the Lyman-alpha photons scattered. And with MUSE, we detected that gas, shown in the color image here in the center. The black contours are the UV star-forming regions, matched with the same resolution. And in the color scale, you can actually see the extended Lyman-alpha emission. So it's a Lyman-alpha halo around a galaxy. And what this shows is that there is basically some neutral hydrogen gas that in which some of the Lyman-alpha photons that are produced in the central component are scattered. So the gas is illuminated basically by these photons that are originating from the center. It's interesting to look at the shape of this halo. We can do that just by looking at it or by modeling, doesn't really matter. It's a bit elongated in the direction of the other components. I think that's not unexpected if you see multiple components of a galaxy being separated in one direction, that the gas structure follows that direction as well. It's nice to see that. We still need to address what the source of this gas is. Is this actually primordial gas that is infalling, or is this actually enriched gas or even stripped in tidal interactions? And from these Lyman-alpha observations, we cannot address that. It would be possible to address that perhaps with metal lines, because, for example, you would expect this extended emission to be more luminous in metal lines in case it's has been enriched or it's basically expelled from the galaxy or is stripped gas instead of primordial. So we hope to observe that in the future. looking at other properties, comparing this Lyman-alpha halo of this redshift 6.6 galaxy to other galaxies, there have been claims that Lyman-alpha halos around very high redshift galaxies are shallower than around lower redshift galaxies. Basically, the Lyman-alpha light disperses more slowly. We actually, that could be a sign of more neutral gas away from galaxies, so the scattering continues out to larger radii. This is actually not what we see. So in this galaxy, we see that the CGM structure being illuminated by Lyman-alpha is actually very similar to galaxies at later epochs. I think that probably indicates that this galaxy, similar to the other one, resides already in a more evolved part of the universe, a more ionized part of the universe. Good. So now the last part, and I see that luckily I have some time to explain that in some detail, I hope. So I've been talking about emission lines all the time, Lyman-alpha, H-alpha, carbon-2, and the reason for that is that those are easier to observe because all the light is centered in basically a few angstroms, or in a few pixels on a spectrograph. If you want to learn something about stars in a galaxy, you need to measure the stellar continuum. It's much harder. And I've been working with the MUSE team on a new data set that's called the MUSE Extreme Deep Field. It's very expensive. It's a 140-hour observation of the Hubble Extreme Deep Field with MUSE. MUSE is an IFU, so it slices this picture in 3,600 wavelength layers with a width of 1 angstrom. So it's a 3D picture. I actually do have a movie because I will actually start it now, and every change you see is basically in different wavelength. So if you are just looking at it, the arrow is pointing towards the galaxy that I'm studying. There you see it appearing suddenly. If you just look at this, you can see emission lines popping up on all different kinds of locations slowly. So it's an extremely rich data set that you can use to study all these galaxies in the field. It looks like a circle because all those 140 hours were slightly rotated after each other. And that's actually very nice to reduce systematics in your data set. It's an observational feature. This data set is currently being used to look at extended Lyman-alpha gas, filaments connecting galaxies. There's a study looking at rotation curves of lower redshift galaxies, quite high radii. But I'm looking at this galaxy shown with the arrow. This is the spectrum of that galaxy, and this is the brightest galaxy in this field at high redshift. It's at redshift 4.8. So the universe is about 1.5 gigayears old. And the signal to noise is really, you don't get that for typical observations. The Lyman-alpha signal to noise is 650, but we're not interested in that here. But we actually have a signal to noise of about 30 in the continuum, which means that most of these wiggles that you see in this spectrum are actually real, and they're not from noise of your measurement. And many of these wiggles are due to absorption from interstellar gas. There are some faint emission lines, but there are also a few features which are from stellar atmospheres. And by fitting those features with models, you can infer the stellar metallicity and the age of the stars in this galaxy. And this is the first time that this is possible for an individual galaxy at such a high redshift. And I think this is nice to do because, in the end, one of the reasons to find all these very distant galaxies is that we want to learn. I want to learn what the properties of the stars in these galaxies are. You can only do that in the end by actually matching the spectra of these stars. Instead of, if you look at the emission lines, you're always sensitive to photoionization modeling. Back to emission lines, we do detect carbon-4 line emission, which is quite rare to detect in distant galaxies. This suggests a very hard ionizing spectrum, a low metallicity. But I want to talk about stellar metallicity, and just to show how this works and what is the constraining power that is shown in this figure. This shows the relative spectrum of the lowest stellar metallicity model compared to higher stellar metallicity models in the colors changing from blue to red. And you can see that there are lots of wiggles in this spectrum, and you can constrain those wiggles to constrain the metallicity. The signal to noise of this data is this gray band, so all variations within the gray band you basically cannot constrain. So from these data we can constrain a metallicity at least lower than 0.2 solar from the overall band. But there are a few features that are more constraining that I'll focus on. And those are the two stellar wind features from nitrogen 5 and carbon 4. Nitrogen 5 is shown on the left. So what these are P Cygni features from winds escaping from very massive stars. Particularly nitrogen 5, you need extremely massive stars to be able to ionize that, to get that, to see that transition. And this is gives a very good constraint on the metallicity. So we could infer a metallicity from these lines, but the issue is that we infer a different metallicity if we look at different lines, which is a bit dissatisfying. The yellow model, which is the best model for the nitrogen 5 line, is a metallicity about 10% solar. It actually predicts a feature that's much too strong for what is observed in the other line, which actually prefers a much lower metallicity. So one way to solve this is by, instead of tuning your metallicity, is tuning your star formation history. Because we assumed here that either we have a single stellar population, basically a single burst star formation history, or continuous star formation history. And both of those models can actually not satisfactorily explain the spectrum of this galaxy. However, if we do quite complex two-component star formation history, so if we assume that the star formation history of this galaxy consists of two bursts, we have some priors on the ages of those bursts that I can answer if you are interested. And those models can actually fit the spectrum much better. And you can say, well, of course, you add more free parameters, you get a better fit. That's true, but on the other hand, there's also additional data that we did not use in the fitting, and the two burst model fits all that data better. The most obvious thing is just the image from HST. It's a clumpy source, and the MUSE data actually does not resolve that source. It actually has the sum of all this light. Then there's also the infrared photometry from Hubble and Spitzer data that's better matched with this two-component burst. And the H-alpha luminosity is better matched. So let's just skip one. So yes, this is a galaxy where we have a good constraint on the stellar metallicity, and I think that's nice. And we can actually compare that as my final slide to learn something about what we should do in the future. In particular, if you want to find such galaxies, because in the future, of course, observational time is limited, and you cannot get such spectra for all galaxies. And if you want to observe very low metallicity stars, you want to select the best targets. And I think this also nicely circles my entire talk, because what we find is that the stellar metallicity, if we combine our measurement, which is the solid red point, it has a big error bar because of the uncertainties on the star formation history. But if you want to find low stellar metallicity systems, looking at galaxies with a high observed Lyman-alpha equivalent width is a very efficient way to do this, because we see a very nice correlation. And that's so that means that the Lyman-alpha equivalent width is a good pre-selector of very young and near primordial systems. Just to add a final note, you see the error bars are very big here. So that's not very satisfying. I just want to show from modeling how much we can reduce the error bars in quite an easy way. As I said, the major uncertainty on this error bar, this is the PDF. So the error bar is basically the width of this PDF that you can see on the left. The error bar is basically because we don't know the star formation history of this galaxy. If we, let's say, simulate similar galaxy with a known star formation history, and then fit it again, we get similar error bars, of course. But then we can ask, what if we actually know the H-alpha luminosity from future James Webb observations? As I said, the H-alpha luminosity is very sensitive to recent star formation. And indeed, if you know the intrinsic H-alpha luminosity, you can basically shrink your error bars on the metallicity by a lot. So that shows that you can basically fix this, the degeneracy between variations in star formation history and metallicity if we have H-alpha measurements. So I think that's a very bright future because these measurements are expected 2 years from now. And I'm just going to leave you with my takeaway points, which are basically the titles of my modules and some open questions that we learned from all these different science projects. I'm happy to discuss more or answer any questions. And thanks for listening.
Okay, thank you, Jorryt. Okay, any questions? So if you do have questions, just just raise your hand, and then we're going to answer that. In the meanwhile, I'm maybe just, I just take the prerogative and ask the first question. You mentioned at some point like different ways of how these Lyman-alpha emitters or certain galaxies are Lyman-alpha emitters or not Lyman-alpha emitters, and to some extent this reminded me a little bit of this question about a unified AGN model. So is there like some arguments to be made for whether being a Lyman-alpha emitter or not is just a geometrical line of as a viewing angle essentially effect, maybe based on the clustering, or is there like some clear evidence that that's not the case, that there's something else that must be different between Lyman-alpha emitters and the other galaxies?
Yeah, I think that's a good question. I actually submitted a proposal to try to answer that. But so I think there is some evidence that the viewing angle is important, because we actually see that all the Lyman-alpha emitters are very compact galaxies. We may be looking at them face on. So that may be the case. And particularly if we compare to H-alpha emitters or galaxies that are not strong Lyman-alpha emitters, they seem to be more elongated. So I think there is something pointing towards that direction. But what you want to do is actually you want to observe galaxies selected irrespectively of their Lyman-alpha emission, and then observe their Lyman-alpha emission. And that's very hard to do at high redshift because it's hard to you want to basically control for the intrinsic Lyman-alpha emission. So you want to ideally control for the intrinsic H-alpha emission, and that's not very easy to do at redshift 3. But we could do that quite easily in the future if we have O3 samples from James Webb. Having said that, so in ongoing work, I did a stack on. I looked at the Lyman-alpha line profiles, which tell you something about how did the photons escape through the gas. And if you separate, so you would expect that the galaxies that have a fortunate viewing angle have a narrower Lyman-alpha profile compared to the galaxies with an unfortunate viewing angle. So I made a stack of galaxies splitting by the profile, the Lyman-alpha profile, which basically means splitting by how the photons travel through the ISM. And in that stack, you can actually still see differences in the stellar the inferred stellar properties. So you still see differences you see that the stack that has like favorable Lyman-alpha lines of sight has younger stars. So that indicates that viewing angle is not the only thing. I think it's a combination of a certain galaxy property, like a young age or a few million years after a starburst, that will enable more viewing angles to be favorable. So you have a combination of a systematic effect and a stochastic effect. I think that will be the answer, but then what's the relative importance of the two is, is the challenge.
Okay, thanks. I think that was a very nice answer. Any questions? You mentioned at the very beginning also that when you look at the star formation rate density, that it's done with a combination of H alpha for, below redshift 2.5, and then if you go to high redshift, I guess because it drops out of HST, you go to Lyman-alpha. So, and then I think we also saw that, the more massive objects are absorbed in Lyman-alpha, so you don't really see them. And so don't we then have a, potentially a strong bias? Are we not missing potentially a significant amount of star formation at high redshift?
If we look at Lyman-alpha, yes. So I think I didn't explain it properly, I think. So this the famous star formation rate density, right? You know what? I'm actually going to draw. Because the Lyman-alpha star formation rate density is not shown here. This is the star formation rate density mostly from UV CONTINUUM. And if you would try to estimate the Lyman-alpha star formation, no, the zoom thing is exactly in the way. If you want to estimate the Lyman-alpha star formation rate density on this diagram, I think it actually would look like something like this, based on the Lyman-alpha luminosity. If you convert the luminosity function to a star formation rate density, so this was actually used this difference was used to argue that the global Lyman-alpha escape fraction increases to high redshift, or the opposite, the global Lyman-alpha escape fraction decreases to lower redshift. And that's exactly because you build up massive galaxies, those have dust, and those are not Lyman-alpha emitters anymore. So you do not want to use this line for a complete census of star formation rate. You do, I think it's still nice to at least have it with emission lines, because if you do it with UV CONTINUUM, there's other issues to worry about. Yeah.
Okay, thanks. Okay, any other questions for our speaker? It seems everyone is afraid to ask, or maybe it was too much information.
Yeah, I should have. I actually got slightly confused with the time, and I thought I have so much time, and then I thought, oh no, I don't have much time. Sorry.
Well, you ended actually perfectly on time. So okay, so I have one more question that I can ask, and that is, so you also showed this kind of relationship, really briefly, between escape fraction and outflow velocity. And at first sight, it seems a little bit strange, right? Because you showed, I think, if you can maybe pull up the slide, that if you have higher outflow velocities.
So this is not the outflow. Right? This is not the outflow velocity.
Oh, sorry. Okay, what is it? What I'm seeing there? The excess.
This is the separation of these two Lyman-alpha lines. And
okay.
This is
okay. Well,
from the model,
okay. So then it makes more sense. Okay, that makes more sense, because if it's broader, then obviously you have more stuff intervening, and so you will have a lower escape fraction, right? Okay, so I think then this question is answered itself. Okay, that makes sense.
Sorry, yes.
Okay. Okay, good. Yeah, because I was wondering, so why is it that, I mean, it could still be that objects which have higher outflow rates have a lower escape fraction. I mean, it would be kind of counterintuitive with the picture that they clear out a path, but who knows, right? So, okay, good. I think I understand it. All right. so last chance to ask any questions for Jorryt. Otherwise, I mean, Jorryt is here. He's a local. You can send him an email, and you know, he's a very friendly guy. So just send him an email if you have any questions about this his work. And yeah, I thank you, to Jorryt, for being here today. And well, good luck with your new proposals.
Thanks.